Here's an example of another improper integral. This one's not so quite obvious that the integral is improper. The reason that we consider this an improper integral is, well, let's think of it in terms of area again. So I've got the graph of 1 over x here, and we're evaluating the integral from 0 to 1. So we could think of that as the area of the region under the curve y equals 1 over x, with x going from 0 to 1. So 1 is right here. Here's x equals 1. X equals 0 is the y-axis, which the graph never quite reaches. So this, again, is an unbounded region. In terms of area, it's this region right here. Since it's an unbounded region, what we could do to investigate whether the area of this region approaches any finite number is to set up a left-hand boundary. So maybe something like this. Call it t, and then let t approach 0 from the right. That will give us a bounded region. So we know that it does have a finite area. We could calculate that area. Let's say we had some way of doing that. And then evaluate or find the area of this region for values of t like 0.1, 0.01, 0.001. So as t gets closer and closer to 0 through positive values. So the way to evaluate these improper integrals when, so the key here is that part of our interval of integration here from 0 to 1 includes an infinite discontinuity in the integrand here. So a vertical asymptote in the graph. So when you've got a vertical asymptote within your interval of integration, then we need to express this as a limit because this is an improper integral. So we write this as the limit as t approaches 0 from the right. We're not trying to approach that asymptote from both sides. We're not even trying to approach 0 from this side, only from the right. So this is a one-sided limit. Integral from, so we replace the 0, which note the 0 is not even in the domain of this integrand. So we're replacing it with t, where t is some slightly positive number, and so that would be in the domain of this integrand here. So the integral from t to 1. Okay, now the evaluation of this integral is relatively simple. I'll include some other examples with some more complicated integrals, or maybe more complicated limits. But in this case, we've already integrated this. The antiderivative of 1 over x is ln of x. So this is equal to the limit as t approaches 0 from the right. Sorry again for the handwriting. I'm still writing with my index finger here. So the antiderivative is natural log of x, as x ranges from t to 1. Now, if it's concerning you that I didn't write the absolute value there, because normally we write ln of the absolute value of x, it's because our interval of integration here deals only with positive values, so you don't really need the absolute value. That would be redundant. You're not wrong if you write it, though. You just want to keep things as simple as possible. Okay, so now plug in the limits of integration. I'm going to leave the limit outside for now, but I'll say something about that in a second. Ugh, okay, that's a limit as t approaches 0 from the right. Sorry about that. Natural log of 1 minus natural log of the lower limit, which is t. Okay, so whenever you're plugging in a finite number, so like we are there with the natural log of 1, so that's always going to be a finite number. We plug a finite number into our integrand, that's always going to give us a finite number, in this case 0. When you take the limit of a constant, it's just equal to that constant. So you don't really have to write the limit in front of the expression where you're actually plugging in a number. The limit doesn't really need to be written there, so that's just 0 for natural log of 1. We only apply the limit to the expression that involves t. Okay, so that's 0 from the right of natural log of t. Okay, now the graph of natural log of x. We're going to need to recall that again. So this is just a good graph to know in general for this section, it seems like. Looks like this. So as t, or x in this case, as it approaches 0 from the right, I'll just use the pointer. Okay. The y value is diving down here to negative infinity. So as the argument, as the input approaches 0 from the right, the output of natural log of x approaches negative infinity. Oops. Negative infinity down here. So this limit over here is equal to negative infinity. And then, I mean, once we see that we've got a value of infinity here, then this integral diverges. But I'll write this out. So we have 0 minus the negative infinity. So technically this limit is equal to infinity. But whether it's infinity or negative infinity doesn't really matter. Either way, we've learned then that the integral from 0 to 1 of 1 over x dx diverges, because we did not get a finite value for the limit.